So another geometric application of integration is in finding the volume of a solid of revolution. So for example, if we have this area here bounded, okay, by the yellow line, the orange line, the x-axis, and the y-axis. So for example, this area here. Okay, so of course we can solve for the area by um, drawing no a strip, for example, a vertical strip with thickness dx, okay, and length y, because the lower end of the vertical strip is touching, okay, the x-axis. So supposing that strip is to be rotated about the x-axis, okay, so the x-axis is what we call the axis of rotation. So what if the x-axis again is the axis of rotation? So imagine what will happen to a vertical strip if we're going to rotate it, okay, about the axis of rotation. So the lower end of the vertical strip again touches the x-axis, therefore the length of the vertical strip is y and the thickness is dx. So if we're going to rotate that, okay, so this will happen. Okay, so this figure will be formed. So it would have a similar strip below the x-axis, okay, because we're going to rotate that about the x-axis. So it will go around no the x-axis. So if it will go around no the x-axis, okay. So imagine no so a circular cross section will be formed. So that circular cross section is this one. So if we're going to view it um at the side, okay, if this side view, then this cross section no is a circle. Okay. So we call this a circular disc. Okay, so the cross section is a circle. So again, we call it a circular disc. Hence the term circular disc method. So if you're going to rotate a vertical strip whose lower end touches, okay, the x-axis, so this circular disc will be formed, wherein again the cross-sectional area is a circle and the thickness, okay, is ADX. So this represents the um the differential volume, okay, of the solid of revolution. So if we're going to get the volume, okay, the differential volume dV, so we make the circular disc as small as possible, okay, and add, okay, all the differential volumes. So meaning we need to integrate, okay, so the differential volume is equal to the cross-sectional area times the thickness. Okay, so since the cross-sectional area is a circle, so we multiply the area of the circle with the thickness dx. Okay, so area of a circle is pi, no, r squared. And the r here for this vertical differential volume, no, the circular disc is y, okay, from this vertical strip here. So the center, or rather the radius, no, of this circle is equal to y. So this is the radius, okay, of the cross-sectional area, which is a circle. Okay, so pi r squared, and again, the radius is equal to y. So we write pi y squared, okay, multiplied by the thickness dx. So if we're going to solve for the volume, so we integrate. So therefore, volume of a solid of revolution, okay, is the integral of pi y squared dx, or we can put the constant outside. So multiply it with y squared dx. So using a circular disk method, okay, so we can solve for the volume of a solid of revolution by using this formula. Okay, take note that this is for a vertical strip, and the lower end of the vertical strip touches the axis of rotation. Okay, and the axis of rotation here is the x-axis. So supposing we make the axis of rotation vertical, okay, let's say the y-axis, then if we're going to use this method, so we need to draw a horizontal strip instead of a vertical one. Okay, and then same thing. So if we're going to use, so let me draw that here below. So if we're going to draw, okay, a strip which is horizontal, rotate it here about the y-axis. So a circular disc is also formed, okay, but it's already in this orientation. So pahigda na siya because our strip is already horizontal. Okay. So let me change that. Okay. Why can't I erase the entire stroke? No. Okay. It's happening for a moment. So a horizontal circular disc will be formed. Okay, so with thickness dy and whose radius, okay, is x since it's already a horizontal strip. So the volume would be, okay, the volume would be pi times the integral of x squared dy. Okay, if it's a horizontal strip. And this one if it's a vertical strip. So for area under a curve, it's y dx if it's a vertical strip, and x dy for horizontal strip. So since we're getting na the volume of a solid of revolution, so it must be of cubic, okay, units. So this must be squared. The y must be squared and multiply it with the thickness. So the unit would be cubic units. All right. So for example, let's continue with this area, rectangular area here. So if we're going to draw more vertical strips, so there would be additional, okay, there would be additional circular discs. Okay, I can also change the thickness. So the representation of the thickness is dx. So if we're going to this or these circular disks together, okay, so from the lower limit to the upper limit, okay, so we get therefore the volume of the solid of revolution. Okay, so let's have some real life application, or not necessarily application, real life example, no examples for this type of solid of revolution wherein the cross-sectional area is a circle. So we have this cucumber sliced, okay, so the cross-section no, is a circle. So this one slice here is what we call a circular disc. So another example is this one, a Silvana. Okay, so we're going to connect all the sizes. So a cylinder, okay, is formed. And if this apple is a perfect sphere, so if we are going to um, cut it into slices, so a circle, a circular cross section will be formed. So the slices would be circular discs. All right. I hope you can imagine the solid that will be formed, okay, by rotating no an area about an axis. So let's have an example. Let's say we derive no, a formula for getting the volume of a solid figure. Okay, so if we have this equation, for example, okay, so a line, um, so line, so we have this linear equation hx plus ry equals rh, where h and r are the coefficients no, of the x and the y terms respectively, okay, and they are constants. So we are going to find the volume of the solid generated if the area is bounded, okay, by this line, okay, and the y-axis bounded by this line and the y-axis, okay, the x-axis also, and our axis of rotation is, let's say, the y-axis. So we plot some points. Okay, we can use the intercepts of the line. So if x is 0, okay, so ry equals rh or y equals h. So the y-intercept is h. And if y is 0, so we cover the y term. So hx equals rh or x equals r. Okay, so these are the points on the line. So we plot them. Okay, so since we do not have a specific number for h and r, so we can just have, let's say, h here and the r here. Okay, so we connect the points. So these are the points on that line. Okay, so the area that we're going to rotate about the y-axis is this triangular region here. Okay, it's bounded by the y-axis, the x-axis, and the given line. So this triangular region. So if we're going to rotate it about, okay, the y-axis, so if you're going to use a circular disc method, so we are going to draw, okay, a strip that is perpendicular to the axis of rotation. Okay, so the one of the ends of the strip, okay, lies on the axis of rotation. We're going to use a circular disc method. All right. So if we're going to do that, so horizontal, okay, horizontal strip. So this is 4 boxes. Okay, so for this part here, so we can draw. Okay, so we can draw this circular disc. Okay, so I don't know what's happening to the Control Z function in my laptop. It's not working. Anyway, I hope you can just imagine lang no the disc. So this is the circular disc. So since we're using a horizontal strip, so manapahigda no ang disc. Okay. So you can also make an extension of the line here. Yes, you can have it in dashes. Okay, again, I cannot use the Control Z. I don't know. Naunsa na ni. Okay. So, dili na symmetrical. So, assuming that is symmetrical, no? So, we can draw more discs. Let's say at this portion here. Okay, we construct another disc with a smaller radius though. Okay, so we add all these discs, no? The volume of the discs formed. Okay, so we add them all up. So basically, okay, the solid figure that is formed, if we rotate, okay, this triangular region, no, is a cone. Imagine lang, no, ice cream cone. Kainit sa panahon, nanindot ikaw ng ice cream. Okay, so if this is covered entirely with slices, no, with circular discs, so a right circular cone is formed. Okay, so since it's a horizontal strip, so in getting the volume, okay, in getting the volume, so pi times the integral of x squared dy. Okay, so of course we put the limits, no? Later we determine the limits. So we have x. Okay, so meaning x from the given equation. So let's solve for the x from the given equation. We should write it as a function of y because our variable of integration here is is y rather, okay, because we are using a horizontal strip. So solving for x, we have hx equals rh minus ry, okay, or x is equal to, we can factor out the r, so r times h minus y, and then over h. Again, take note, r and h are constants. Okay, so you plug this into the integrand expression. So x is r times h minus y all over h. Okay, you need to square it and then dy. So we have pi, okay, times the integral of, so we distribute the power so that we can put the constants, okay, outside and just focus on the one with the variable, no? The one with the y. So this is also squared. dy, r, and h are constants, so we can put them outside. Okay, and what's left is h minus y quantity squared dy. So we can have this expressed as u cubed du. So we let u, okay, be equal to h minus y so that we can write it as u squared du. Sorry, I said u cubed. No, it's u squared du. So h minus y is the u. So du therefore is 0 minus 1. Okay, h is a constant, so its derivative is 0. So 0 minus 1, or that's negative 1, okay, dy. So we need a neutralizing factor, negative 1. Okay, so we can put that negative sign here before the constants. Okay, and then this is now converted to u squared du. So integrating it, so it's basically 1/3 u cubed, right? So times 1/3 u cubed, okay? And then supposedly plus c, no? Pero we need to evaluate it, okay, from a lower limit to upper limit. So it's a horizontal strip, so we must be using the y values. Okay, so our lower limit would be from this point here, so meaning 0, and the upper limit is this point here, the y-intercept, which is h. So we evaluate from 0 to h. Okay, so let me write the limits here. 0, or since it's, yeah, we can write it as 0 to h here. 0 to h, 0 to h. Or you can put the limits on this part of the solution. Just make sure to no, indicate what should be the limits. So at y, okay, especially if we're changing no, the variable. So the y here is the h. Okay, so if ever you will be changing it to another letter, okay, so it would not be consistent if we are going to put here 0 and h. We need to solve for u, okay, if we are changing no, the variable. So you can just omit the limits, and then once you go back to the original variable, so you can put na the limits. So let's put this back, no, the h minus y back first before evaluating no, the integral. So negative pi r squared over h squared. Okay, it's times 1/3. So we can also just, yeah, later na lang. Nato ibalhin ang 1/3. So 1/3 times h minus y quantity cube. Or that's negative, okay, 1/3. Yeah, negative 1/3 pi r squared, okay, over h squared, and then h minus y quantity cube. So evaluate 0 to h. So at x equals h, so these are constants naman. Okay, so we can, or it's a common factor, no? In evaluating at h and at 0. So we can just factor that out and then proceed to the evaluation of the integral. Okay. And then minus h minus 0, no? The variable here again is y. Okay, so you need to put the h to the y term. So you can factor that out. So meaning, okay, evaluate ni mo pod, okay, at h or at y equals 0. So h minus 0 for the second value. Okay, or you can also put again the minus negative 1/3 pi r squared over h squared. Pero again, I am factoring out that one because it's common naman no to bali both um terms where y is h and y is 0. Okay? So, akong ibuhat ana ha, evaluating the integral at h minus the integral at y equals 0. Okay, so i-factor out lang si negative 1/3 pi r squared over h squared para one time lang nimo isulat. So h minus h, this is equal to 0. Okay, this is equal to 0 cube. And then this is equal to h cube. So bale, it's negative 1/3 pi r squared over h squared, okay, times h cube. So we can, okay, times negative. So kalimutan sa na negative, no? Mana careful good if there are subtraction operations. So this is 0 minus h cube. That's negative h cube and dili ra h cube. So the volume, of course, must be positive. Okay, so negative h cube times negative 1/3 pi r squared over h squared. So to simplify that, it's positive 1/3, okay, pi r squared times h. So h squared is a common factor. So the volume, therefore, of the solid of revolution formed by rotating, okay, the area, no, the rectangular or the triangular area here, okay, is 1/3 pi r squared h, which is the formula in getting the volume of a right circular cone. Okay, with r being the radius of the right circular cone and h is the height. So that is how the formulas, the I know of solids of revolution, okay, are derived, no, using integral calculus. So up next is another method of getting, okay, the volume of a solid of revolution.